online about 61850. And this is what he has said. We are in the process of adopting 61850 for our next generation substation automation. This is what it's going to do for us. Okay, this is not coming from, this is a user that's saying this, will result in measurable engineering, operations, and maintenance benefits through cost reduction, reliability, and safety. And how are they doing that? With process improvement, enhanced security, of course, configuration management, and interoperability. So that's right out of those are the words of a utility engineering manager that's doing this. Okay, I'm not going to take any time on this. Just there are some things that are continuing on from SGIP activities, but I think I'm out of time, so I think I'll wrap it up, and this will be in the slide set. So, all right, thank you. Any questions? Can I take any questions right now?
Any clarifying questions, please? Maybe one or two. If not, we'll proceed.
Okay, back on schedule. Yeah. Did you get the file? Oh, yeah. Okay. Put this on. Let me turn it off.
Okay. Thank you, Ron. Putting me back on time now. I can take all that extra time you gave me. So, Ralph Makowitz of Cisco. Wanted to do a presentation here to just give you an idea of what 61850 looks like. With this, we're going to be talking about the core standard here. When you look at the slides later, the materials that are uploaded, you'll see a lot more than what's being presented here. I wanted to give you some good reference material, so there's a lot more than what we have time to cover today that'll be handed out and available on the NASPI working group website. But we're going to kind of go through these topics here, give you a pretty good understanding of how the core standard works. And in a little bit later, Mark and some others are going to talk a bit more about the synchrophaser profiles. So, what is it with all these model things? Everybody keeps talking about models and how these IEC standards fit together. Well, we're being driven by a desire to achieve interoperability and integration of systems, and that's basically systems can talk to each other and cooperate and perform some kind of a useful business function. And we know it's very easy to achieve this. All it takes is enough time, money, and effort, and you can make anything integrate and interoperate. Well, the idea here is there's a better way. What we want to do is we want to be able to achieve interoperability and integration without you having to write the code for everything from scratch every time you want to achieve this. And you have to have standards to do that. And that's really what the IEC standards are about. That's the focus of that activity that's occurring there, is being able to achieve that. And they have a way of doing that by looking beyond just the communication protocols, but because the protocols themselves don't really address the integration dilemma of how you make systems cooperate with each other. Simply being able to exchange a value doesn't cover everything needed to achieve integration. And that's, again, what the 61850 standards are about. It's a strategic vision for using modeling, abstract modeling, to define the integration space, followed by applications of those models to specific profiles and protocols that you can apply and build into your systems. And at the same time, addressing the security aspects across the board. So this is kind of a little bit of a busy slide here, but the idea, this is the TC57 architecture. And if we look over here, you can see we have the SIM covers, the Common Information Model covers a large area. 61850 is involved in the communication part, and we also have ICCP. And the 6870-5, the DMP equivalent of IEC, fits in here. And security goes across the entire space. So if we look at, well, traditional protocol standards basically defined how you arranged bytes on the wire to exchange a piece of data. And so you say, well, that worked. That did work. It dramatically lowered the cost to actually achieve interoperability between two devices. but it didn't really cover everything needed for integration because it didn't define the data representation. How devices organize data was always differently. So you achieved some interoperability, but not integration. So the typical legacy protocol would say, yeah, we have a very simple little model. We organize data in a big sequence of array. Now this could be register numbers, index numbers, whatever. But the problem is that you're not thinking about register 22. You're thinking about, I need a phase A voltage. So there's no power system context in these numbers. So to solve this problem, a new approach is needed where it's not just specifying the bytes on the wire. Of course you have to have a protocol, but also about the meaning of the data in a more standardized way to represent it. And the behavior of a device is when you communicate with it, what is the device supposed to do from a behavioral perspective? And that's what 61850 tried to address. It started with a new approach to saying we're going to start with abstract modeling of the problem space. We're going to make devices have a model for how they represent data, a model for how they behave when a client communicates with that device, what are the actions that device takes. We're going to have a way of describing the configuration of devices so that devices and tools can exchange information between themselves. And we're going to take those abstract models and map them to a variety of different profiles to meet a variety of different use cases. And also, because now we have these abstract definitions everywhere, we can define standardized conformance test cases as well. So with the legacy approach, if you have an application that wants to be focused on power system functions, you had this process that you had to do, mapping with spreadsheets, databases, where you took your power system engineers and you had them essentially edit spreadsheets. It was a necessary function, but it's all cost, no value. With 61850, there's a model that defines how you find data in the device that's consistent across all the devices. And we'll go into a little bit more detail in this in a few minutes about how we start with a physical device. We have logical devices within that physical device, logical nodes, which might represent a circuit breaker or a measurement unit. And within those, you might have phase to ground voltages, amps, and in which case you end up with an object name that has meaning that's in the context of a power system function. So what this means is when you sit down and you want to use this technology in an application, you're not mapping it, you're dealing directly with power system context. You understand by simply accessing and looking at the point exactly what you're dealing with. What is that piece of information? And if, depending on what the brand or the function of the device is, the names are basically the same. In this case here, we have brand X and brand Y. You have an instantaneous overcurrent relay versus a differential relay. They'll have different protection functions in them, but if they're both providing you a phase to ground voltage measurement, the object names for those two are the same, regardless of the function or the brand. So with some minimal training, you can learn to understand what the power system context is for any 61850 device. The standard itself is layered into an abstract definition of object models followed with services that are used by clients and servers to exchange data using that model. And then there's a mapping of those abstract contexts to a specific protocol. The first protocol is mapped to is 8.1. It's the MMS protocol per ISO 9506. And that's what people communicate with over the wire. Now, the advantage here is that by separating the abstract and the physical mapping out, we can take those abstract concepts and map them to a different set of services. And for instance, there's an 8.2 underway to consider a mapping of those services to web services, for instance. Now the advantage here now is that you have the same abstract concepts and perhaps you're addressing different sets of use cases with a web service interface compared to perhaps a real-time automation use case that's occurring inside substations. One of the other protocols we're all familiar with that's an IEC standard as well as ICCP, the Inter-Control Center Communication Protocol. It's really, the primary use case for this has been external links. Now, the ICCP is used extensively inside utilities as well for systems to where those interfaces are readily available. But the protocol itself was designed for this use case where you're dealing with communications between entities. So you have this concept of bilateral configuration where both sides have to agree on a data exchange before the data flows. Well, with 61850, the idea is to automate the configuration process, eliminate bilateral configuration to make it easier to set up and get devices communicating and data exchange to happen internally. So the other IEC standard I want to just give a brief review of is the Common Information Model. It's an object-oriented model of the power system. It's basically a way of transferring the physical construction of the power system, of the wires, the poles, the insulators, the transformers, the power plants, the generators in the power plants, the circuit breakers and switches, and describing this in an object-oriented unified modeling language, a UML model, that computers can understand, so that now you can exchange this information between applications. So the application that understands one part of the power system, you can communicate that electronically to other applications using the SIM. So you might say, well, what do I need the SIM for? I got all this, why do I want this complexity? I got to learn modeling now. And when we look at typical systems where you're comfortable with basically tag naming, it's simple. You got to look at the problem that's trying to be solved. Now, most people will say, okay, well, I got power system data, I got a SCADA-MS, well, how do I get data in there? But you have to consider, is this really the problem that's trying to be solved? Is this a valid architecture, or is this really the kind of architecture we deal with on a day-to-day basis? This problem is very difficult to solve with tags compared to a model. So that's really what we're talking about when we look at what does this cost, all this complexity, etc. Well, to try and do this with tags, the complexity of that solution is by far unmanageable and really can't be done. This is the kind of problem space where we're trying to make it effective in small applications, but yet be able to build this up and handle the complexity of very large scale systems. You know, we scale this up to the smart grid where we're dealing with millions of data points. Just think about 15 seconds to configure a tag, 26 man years to configure 2 million meters. I doubt anybody can manually configure a tag in 15 seconds anyways. And if you look at scalability, just consider that this drawing right here, if I drew this as little boxes in PowerPoint, it would take 5 or 6 seconds just to draw that on this screen. And this is just a drawing in a PowerPoint slide. Try to imagine trying to scale our systems up to the point where we're dealing with 2 million different tag names. It becomes a big problem. So that's what SIM's about. SIM is about providing detailed power system topology, but also modeling assets, consumers, loads, the financial and scheduling transactions associated with energy markets, work management, of course, and SCADA and measurements. 61850, on the other hand, is more device-oriented and looking at device models, service models associated with communicating to the devices. Now, they do overlap somewhat. SCADA and measurements, object and data naming conventions naturally fit together. But there's also some overlap that needs to be resolved if we're going to have bidirectional data flow between power system automation tools and that are dealing with 61850 and modeling systems like EMS, et cetera, that are doing large-scale systems. And that's one of the activities that's going on right now is the SIM 61850 harmonization activity, to where much of the systems are compatible because they don't overlap, or they're compatible with each other inherently. And where they do overlap, we're doing a harmonization process to where we can go back and forth between these two models using a process. So we're not rewriting SIM, we're not rewriting 61850, we're just allowing a mechanism to allow us to get back and forth between these two systems. So that's just kind of a brief review of 61850, how it fits into the IEC standards. Wanted to talk a little bit about the engineering process of 61850, because one of the things that's unique about 61850 is, in fact, the ability to have a positive impact on the business process, to where you're not just simply providing a new way to communicate to a device, but you're enabling new, more productive ways to approach the engineering and design processes of building and deploying power systems. And that's where the huge, significant cost impacts can occur beyond just one protocol that's more efficient than another protocol. If we can make a big reduction in the amount of power, the process of building power systems, we're talking about going from a place to where not only does it lower the cost for us to do a substation, but we can do more substations with the same cost and build better systems overall and have a much more positive impact on utility operations. So one of the things at 61850 the process does is starts with a power system design, of course. So the technology that exists to define power system, the relationship of how bays and breakers and switches are interconnected with the transformers and etc. Then there's a process by which you assign the protection functions associated with these things and assign the protection of instantaneous overcurrent, for instance, on a transformer or a breaker, etc. Then the next step in the process is to assign these functions into the specific IEDs that you're going to use within your power system. Tie them together via a network and a communication protocol that allows the data to be exchanged and the functions within these devices to integrate with each other. And then, of course, visualization for the engineers to be able to access the information, see what's going on in the system. They have the tools to adjust the settings, etc., that they need to keep the systems operational. And that's really what 61850 is about, is using the protocols with the ability to exchange the configuration information to tie all the aspects together of building power system automation and to have a very positive impact in lowering the cost of building of the process of what it takes to successfully plan, implement, design, and build power systems. And that's the unique thing about 61850. And we'll, at the end of the presentation, we'll talk a little bit about SCL. And I know there's some other presentations that have a more illustrative examples of how this gets applied in real systems. So for here, the profiles, one of the aspects, of course, that's always of interest is, well, how does 61850 work over existing networks? Essentially, there's two ways that 61850 communicates. There's a client-server model to where this is called directed communications, where it's peer-to-peer. A client establishes an association or a connection to a server, and over that link, the client can issue control commands to the device. It can receive reports, poll for data, change settings to do things that are between two peer entities over a network. There's also a multicast type of communication environment to where the devices can simply publish the information that they have about their status and communicate that status very, very fast to many, many different devices and applications quickly. So the idea here is that if you have a server that's publishing information about itself and what state it's in, other devices that need to know that state can receive that information quickly and make control decisions at the level below what a client is involved in. So you're not waiting for SCADA type scans to occur to decide, well, I see the current flow is starting to increase in a particular bus. Perhaps I need to start making adjustments. No, we're talking about things that happen in milliseconds for protection so that you can implement blocking, interlocking, and things of this nature right down into the devices and fundamentally replace the hardwires that are so costly to build into substations. And the way this works is with a variety of different profiles. Time synchronization is, of course, critical, especially in the synchrophaser area, and this is the edition 2 of 61850 and the profiles it supports, and that's the IEEE 1588 time sync profile. And then for the client-server communications, for the core services, which are the control functions, the reporting, the polling functions, they use the MMS protocol over a profile called RFC1006, which runs over TCP/IP, and over Ethernet for communications between clients and servers. Now, I also show TLS in there, Transport Layer Security. This is used for encryption and authentication, so there is a profile where you can use those client services over a secured link. And for multicast, we have a couple of new profiles that are available. We have the traditional profiles of sampled values and goose that go directly to Ethernet. And that's been designed primarily for a single substation type of application, although there are systems that can distribute that over wide area networks. But what's emerging now is with the 90-5 profile that Mark's going to talk about in more detail here is the ability to use IP multicast technology to send that data over wide area networks on a very large scale, taking advantage of some of the internal router protocols that exist for distributing multicast information over large-scale networks, being able to scale that up to the size of NASPI to be able to support large-scale multicast networks, as well as addressing how do you secure that kind of communication using what's called the GDOI standard. And again, there'll be more details on these standards later on when we talk about 90-5, but there's a method to use to obtain the symmetric keys that can be used to encrypt the communications so that the data that flows over that network can be secured and authenticated. So, models. This is just a high-level drawing of a 61850 object model. The physical device is represented by a server function. The servers are essentially the devices that protection relays, RTUs, breaker controllers, things of this nature. That's what the physical devices are. So within a physical device, you would have one or more logical devices. And what's typical in this area is that the manufacturers of devices will organize related functions into different logical devices. For instance, they might have all the protection functions in a logical device called protection. They'll put the measurement functions in a logical device called measurements. They'll put the control functions in a logical device called controls. So this allows you to organize the data so that you can find things a little bit easier when you look at these devices. I also put a little dotted lines there that there's no reason why you can't have client functions in these same devices as well and provide bidirectional communications between clients and servers as well. Within each logical device, you've got these things called logical nodes. And a logical node is a representation of a power system function. Quite just simply, that's what it is: a circuit breaker, a transformer, a switch. And each logical node contains one or more pieces of data. That data can come from field signals that are connected in through the I/O on the device. It could be coming from a process bus connection. For instance, if you have merging units, as Ron talked about before with the process bus, you could get I/O signals from a shared network where everybody's getting the same I/O signals. Or you can have a legacy device, some external device that you're communicating to, that's providing communication to that device, and so what you do is you see the I/O from that device as a 61850 device. And the nice thing about 61850 is it allows this kind of modeling to exist. So it abstracts away where the physical source of the signals come from the way that you communicate those signals between clients and servers. So a logical node is really just a grouping of data associated to a power system function. The data itself is organized in what's called common data classes. What's a logical node? Breakers, current transformers, power transformers, circuit breakers, switch controllers. There's, what is it in the new standard now, 180, I think, some logical nodes defined for many common power system functions as well as common control functions like generic process control and many, many things that are defined. Wind turbines, DERs, batteries, generators, etc. So there's a very comprehensive listing of logical nodes, which we're going to show some of them here shortly. A common data class describes the structure of the logical nodes. These are complex objects that are defined in a tabular way, so actually if you ever get the standard and you go and you look in it and you read this thing, it's actually understandable. Some of the examples of what's a common data class: a single point status, a Boolean point, if you will, or a double point status, to where this perhaps is the position of a circuit breaker, which could be not just open or closed, but also transient or invalid, and as well as numerous other common data classes. Here's a kind of a list. We're not going to go through all these in detail, but just to show you some of the things that exist. There's a variety of different status classes: double point, single point, integers, protection activation, measured values and complex measured values and sampled values, both phase to ground and phase to phase measurements, sequence, harmonic values. Controllable points, things that can be modified by the client via the control model. Settings. This is information you provide to the device that controls its behavior and its control functions: integer settings, time settings, curves, analog set points, etc. So if we look here, this is what's called a single point status. This is the definition of a Boolean point in 61850. And we have this column here called mandatory and optional, and essentially everything that's M is mandatory, everything else is optional. So the whole object may look very complex, but in fact it boils down in practice to a relatively simple object that's got a status value, which is true or false, a quality, and a timestamp. So every object that has a value that's determined by or associated to some field signals has quality and timestamp associated with it, and it's mandatory along with the value. With 61850, though, you also have some other interesting parameters, and these are description fields, to where you have, for instance, the ability to put a description in on an object and describe it in text or in Unicode, so that, for instance, you know, our people in China and other areas of the world that have non-Latin characters, they can also use their languages to describe these objects. And we also have these very interesting attributes that tell us about the namespace of the object. They are optional, but these are important attributes, because if the supplier or the developer of that object has provided some proprietary extensions to it, these objects here tell you that, in fact, there's a proprietary extension of this object. So it gives you the information you need to be able to understand the context of the object. All that information is available to a client by querying the device. If we looked in here, we see this thing called a functional constraint, where we have status values, descriptions, extended values. These are what's called functional constraints, and they're really ways to organize and characterize the specific attributes of an object. The single point status is a relatively simple object, so you don't see too many of these functional constraints. When we start looking at more complex things like measurements, you'll see the value in being able to organize the measurements separately from the configuration parameters, separately from the status values, and so on. And it's just a way to functionally organize the data. So look at a double point status, where before we were dealing with a Boolean on-off status value. Here we have for a double point status, you have 2 bits to represent the status. Typical for instance, a circuit breaker: intermediate, off, on, and bad. So the value, instead of being a Boolean, is what's called a coded and enumerated, and it's a 2-bit pair. So you end up with 4 values. A double point controllable introduces a new concept called controls. And here we have a control value. So we still have the status values, the quality, and the timestamp, which are the ST functional constraint, the status values. But now we've introduced controllable parameters. So a device could issue a control command by writing to the control value to cause a control to occur. And another interesting thing is we have here an object in the configuration functional constraint that tells the client how complex the control procedures are that this device supports. So you can do a direct operate by just simply writing the control value, or a select before operate, which requires you to do a select process before you can operate it. So again, this information is available to the client so that you can discover what it is that's required from the device for you to be able to integrate with it. One of the big advantages of 61850 is there's a lot of information about the device you're communicating with. For instance, in this case, a logical node nameplate is one of the common data classes that exist. In this case, this is giving you information about the logical node itself. And here we have information such as vendor, the software revision, a description, and three very important parameters that give you revision information about the configuration of the device. The configuration revision tells you if the device, the semantic nature of the device has changed or not. If you're communicating to a logical node and the value is 1, and the next time you communicate the value becomes 2, this tells